My name is Emily First, and I'm a PhD student at the University of Massachusetts Amherst. Today, I'm going to talk about my paper, TacTok, Semantics-Aware Proof Synthesis, which is joint work with Yuri Brun and Arjun Guha. This work lies in the field of formal verification of software. And on that note, I want to start off with a claim that I hope we can all get behind, which is that formal verification of software is important. This past year, Ringer et al. Conducted a survey of formally verified software, where they motivated its importance, stating, formal verification of a program can improve actual and perceived reliability. It can help the programmer think about the desired and actual behavior of the program, perhaps finding and fixing bugs in the process. It can make explicit which parts of the system are trusted, and further decrease the burden of trust as more of the system is verified. Now I'm going to turn off my camera so we can focus on the slides. Just a few examples of substantial verification efforts include a formally verified C compiler, an OS microkernel, and a verification framework for distributed systems. Unfortunately, though, formally verifying software is a difficult task. One way to measure its difficulty is in lines of code. Verifying the compiler, for example, required 35,000 lines of Coq, which is the language that could be used for building verified software systems. The certification effort itself is about 8 times bigger than the code it proved. Similarly, the OS microkernel required 480,000 lines of specifications and proofs in Isabelle, another language used in verification. Another measure of difficulty is the expertise required. For example, in building a framework for verifying distributed systems, Wilcox et al. Noted that few practical distributed system implementations have been formally verified, since real-world implementations often diverge in important ways from their high-level descriptions, and so expertise in the system itself is necessary. To ease this burden of verification on programmers, the holy grail would be if one could instead automatically synthesize proofs of software correctness from scratch. Typically, the process for writing these proofs is anything but automatic for the programmer. Suppose, for example, you are writing a program for adding natural numbers, and your specification says this, that addition is associative. You want to formally prove that your addition code satisfies this associativity property. So, you can use an interactive proof assistant to do this. For this work, we're going to focus on the Coq proof assistant. You can power up the Coq IDE, which is a front-end interface for the proof assistant, and start by defining the natural numbers nat using a unary encoding, where you define 0, and then the rest are defined using the successor operator s. Then you define your function for adding natural numbers, which here is a recursive function, and you denote its shorthand n plus m. The AST theorem defines the associativity property for all NMP. You then start to write the proof script, which when completed and run will generate a proof for the theorem. The proof script is made up of proof tactics. This tactic here, called proof, is the starting tactic for the proof script. When the tactic is executed, Coq provides feedback in this window. This feedback is a high-level view of Coq's internal proof state. Here, the proof state consists of a single goal, which is the theorem itself. You as the programmer provide Coq with proof tactics to help it manipulate this proof state. So if you examine this proof state, you see that the goal is a statement that holds for all NMP. So the natural next step is to assume the existence of some arbitrary NMP. You can apply the intros tactic to eliminate the for all quantifier, introducing 3 new variables as assumptions in the proof state. Since add is inductively defined, it is natural to perform induction on one of these variables. Here you induct on n, which leads to 2 subgoals, one for the base case and the other for the inductive case. You can continue applying tactics to prove the subgoals, and you eventually get to this trivial equality, where the left and right-hand sides are identical. You could just apply the reflexivity tactic to solve it, and you end up with no more subgoals. Now, you can complete the proof script with QED. The key observation we make from this proving exercise is that the interactivity in Coq, while taxing for a programmer, can give us a leg up in building a model to be used in automatic proof script generation. This model can use both the proof script and the proof state together in making predictions, as we do in TacTok, which I'll talk about shortly. As we just saw, the programmer and proof assistant are engaged in a conversation of sorts, but prior approaches only consider distinct sides of this conversation in their proof script models. Prior work, such as ASTactic by Yang and Deng and GamePad by Huang et al., have used only the current proof state as input to their proof script models, and then used their models to predict the next tactic. Other researchers, such as Hellendorn et al., have explored only using the proof script tokens thus far as input to their proof script models, and then use their models to predict the next token. Some key results of our work is that TacTok is complementary to prior tools ASTactic and CoqHammer. ASTactic, as I mentioned on the previous slide, is a deep learning approach that only considers the proof state as input to its proof script model. CoqHammer, which is the state-of-the-art tool for Coq, takes an entirely different approach. It doesn't generate proof scripts, but rather produces proofs in Coq's logic ALINA. It does so by performing efficient automated reasoning using facts from a pre-existing library. And so we see together with ASTactic, TacTok can prove 20% more theorems, and together with CoqHammer, TacTok can prove 11.5% more theorems. Taking prior work into consideration, we create novel automated proof script synthesis tools. First is a tool that models the proof script and proof state together, called TacTok. We also create a tool that models the proof script and the target theorem together, called SeqOnly. Lastly, we build tools that use the frequencies of tactics from a set of existing successful proof scripts. The tool WeightedRandom randomly adheres to the observed distribution of these tactics, while WeightedGreedy always selects the most frequently observed ones. These tools, along with ASTactic, fall into the category of metaheuristic search techniques. For the task of proof script synthesis, metaheuristic search techniques search the space of all possible proof scripts using a model that biases the search towards the likely proof script steps. Proof script features serve as input to some model. We'll make it a black box here. The model predicts the next step of the proof script. Here, if we do beam search with a beam width of 3, the model predicts the 3 most likely next steps. These next steps are applied, giving us 3 new candidate proof scripts. The candidate proof scripts are then evaluated based on some success criteria. If, for example, a proof script compiles and there are still goals left to prove, we then continue to search on that proof script. If the proof scripts fail to compile, but the proof state remains unchanged, we then ask for more predictions from the model and try again. If a candidate proof script has no more subgoals, then we apply QED. We've successfully found a proof. Of course, this whole process requires the model to be fairly accurate at predicting the next step of the proof. It doesn't need to be perfect. That's what search is for. But if it's imprecise, we'll get lost in this giant search space and never get to QED. So this brings us to the model that we built, the TacTok model, which consists of a proof state encoder, a proof script encoder, and a tactic decoder, and I'll explain each briefly now. The proof state encoder is from prior method ASTactic, where they encode the underlying ASTs of the proof state terms using a tree LSTM, and then generate embeddings for each. The proof script encoder considers the sequence of proof script tokens. Tokens in the proof script are tactics, their arguments, and punctuation. We can parse this sequence of tokens in different ways to extract different types of information. We can parse such that we only consider the sequence of tactics, or we can parse such that we consider the entire sequence of tokens, except punctuation. And then we can encode this parsed sequence of tokens using a language model. A language model predicts the next token given a sequence of tokens. To encode the proof script sequence, we need to choose a neural language model with trainable parameters so that we can generate an embedding. Here we choose a bidirectional LSTM and it generates an embedding for the sequence. The tactic decoder decodes the next tactic as an AST. Yang and Deng do this in their ASTactic model. However, in TacTok, this decoder is conditioned on both the proof state and proof script encodings and uses them to predict the next tactic AST. This AST has a high-level tactic statement associated with it that can then be applied in a proof script. The model for the SeqOnly tool that we build has the same components, except the only proof state term encoded is the target theorem. To train and evaluate TacTok, we use the CoqGym benchmark dataset, introduced by Yang and Deng. This dataset is the largest available collection of Coq projects. The training set includes 96 projects, consisting of 57,719 human-written proof scripts. The testing set we evaluate on includes 26 projects, consisting of 10,782 theorems, and their associated human written proof scripts. The projects in this set range from having 2 to 2,127 theorems. We first look at TacTok compared to other metaheuristic search techniques. Here we have a Venn diagram showing the number of theorems from the test set that TacTok, ASTactic, and SeqOnly have proven, where the numbers in parentheses are the percentages of the test set. We also have a table of the overall success rates of each, with TacTok proving 12.9%, ASTactic proving 12.3%, and SeqOnly proving 10%. We see that TacTok is able to prove 180 theorems that the other two tools cannot prove. We also see that TacTok is complementary to ASTactic by looking at its added value over ASTactic, which only proves 1,322 theorems total. TacTok is able to prove 264 theorems that ASTactic fails to prove, giving it an added value of 20% over ASTactic. We see that both TacTok and ASTactic outperform SeqOnly, which only proves 1,077 theorems total. TacTok is able to prove 592 theorems that SeqOnly fails to prove, giving it an added value of 55%, while ASTactic proves 553 theorems that SeqOnly fails to prove, giving it an added value of 51.3%. We also look at the WeightedRandom and WeightedGreedy tools, which consider the frequencies of the tactics in the training set. These tools also underperform TacTok, with success rates of 6.2 and 9.7%. We now compare TacTok to CoqHammer. While CoqHammer does outperform TacTok, proving 2,865 theorems, so 26.6% of the test set, TacTok is able to prove 329 theorems that CoqHammer fails to prove, giving TacTok an added value of 11.5% over CoqHammer. Also, TacTok is able to prove 115 theorems that both prior approaches failed to prove, giving TacTok an added value of 3.6% over both tools. Recall that the proofscript encoder could parse the sequence of proofscript tokens in different ways. When we parse the sequence of tactics, we train the Tac model. When we parse the sequence of all tokens, we get the Tok model. These models are trained separately and make up TacTok. If we compare the two models, Tac's added value over Tok is 19%, while Tok's added value over Tac is 25.3%. This suggests that modeling the sequence of tactics is complementary to modeling all tokens, and this complementarity is the prime reason that TacTok relies on both. Here are a couple of theorems from the testing set. Both of these theorems require induction. The first theorem in particular has a nested for all, and so it's expressed using higher order logic, making it more complex than theorems expressed in first order logic, such as the associativity theorem from earlier in this talk. Because these theorems require induction, CoqHammer simply cannot prove such theorems. But TacTok uses a more general approach of learning from human-written proof scripts, and so it can prove such theorems. Not only theoretically, but in fact, TacTok did prove these theorems in our evaluation, whereas CoqHammer and ASTactic did not. Now, with respect to related work, I've already talked about prior work in proof and proof script synthesis throughout my talk, and there are others described in more detail in the paper. Metaheuristic search has been widely used in software engineering, such as for test generation and program repair. We have shown that it can be quite fruitful in proof script synthesis as well. Language models have been very successful in natural language processing applications, such as text generation and machine translation. And there's extensive work on more intricate models than what I've described today, which may provide avenues for further improved modeling of proof scripts. To summarize, I presented TacTok, a tool that models proofscript and proofstate together to automatically synthesize proofs from scratch. I've also presented other novel metaheuristic search techniques, namely SeqOnly, WeightedRandom, and WeightedGreedy. And lastly, I have detailed a large-scale evaluation on 26 Coq projects where we evaluate against prior tools CoqHammer and ASTactic. Our evaluation provides evidence that proofscript and proofstate semantics together provide useful information for proofscript modeling. And the concrete approach I presented for jointly modeling these two types of information can serve as a basis for furthering the creation of automatic verification tools. Thank you.